Hi everyone, I am Shuvomoy Gupta. I am a PhD student at the MIT Operations Research Center. And today I am going to talk about BnB-PEP, a unified methodology for constructing optimal optimization methods. This is a joint work with Professor Bart and Parys at MIT Sloan School of Management and Professor Ernest, who is at Seoul National University. Now, what is BnB-PEP? So BnB-PEP is abbreviation of branch and bound performance estimation programming. The paper that I'm going to talk about, you can find a preprint at this link, and you can find the open source Julia code for our paper at this GitHub link. So I will start with the take-home messages before I dive into the details. So the take-home messages for my presentation is as follows. So we know that large-scale optimization and machine learning problems are often solved by first-order methods. In fact, they're the most popular type of algorithms that we use for deep learning. So naturally, we are interested in finding the optimal, that is the fastest first-order methods. And BnB-PEP is a unified methodology to find that. So it will find you the optimal first-order methods, and it is applicable to many setups, such as convex, non-convex, smooth, non-smooth problems. So what does BnB-PEP do? So first, it shows that the optimal first-order methods for a given setup is itself a solution to certain kind of optimization problems. Not only we can formulate the process of finding the fastest method itself as an optimization problem, we can also solve those optimization problems. So to solve those optimization problems, BnB-PEP proposes a custom branch and bound based algorithm to solve finding the optimal first order method. BnB-PEP will find the fastest method, and in the process of finding it, the optimization problem that we are interested in solving, it will be solved to certifiable global optimality by our custom branch and bound algorithm. Not only that, we can do it in a practical timescale. Furthermore, for all the applications that we consider in our paper, BnB-PEP is able to find a first-order method that outperforms the state-of-the-art results. Finally, BnB-PEP provides a way of systematically generating mathematical convergence proofs under potential function setup, alongside, besides finding also the fastest algorithm in that setup. So of course, I will go into the details how BnB-PEP does that. So I will show two examples of what BnB-PEP can do. So the first example shows that how BnB-PEP finds the best memory-free gradient method in smooth convex setup. So I will discuss what is going on in more details soon. But what this figure actually shows is how the convergence rate of the fastest algorithm compares with the previous state-of-the-art method. And the lower is the convergence. So in other sense, the red curve, which corresponds to BnB-PEP, you can see that it's actually lower than that of the previous state-of-the-art algorithm's convergence rate. So lower is better. And the algorithm found by BnB-PEP, you can see that in a scaled y-axis, it is actually performing quite better compared to the previous state-of-the-art. Another example that I will discuss down the line is how to generate mathematical convergence proof using BnB-PEP. So what this theorem says at this point does not matter too much. So it is the theorem which is proposing a certain kind of first order method, a certain kind of potential function under which we can establish certain kind of convergence rate on the rate of finding a stationary point. And this, what appears below, is a mathematical proof for this theorem. However, what is interesting is that the proof itself is completely generated by BnB-PEP. So, and not only that, the rate that we find in this specific setup turns out to be faster than the previous state of the art. So, okay, so now let's start the presentation earnestly. So this is the outline. So first, I will talk about the background. necessary to understand what BnB-PEP is trying to do. Then we will dive into how BnB-PEP works. So it works in two phases. First, the formulation phase, where it formulates the problem of finding the best method as an optimization problem itself. And then comes the solution phase, where we focus on how to find the globally optimal solution to that optimization problem. Then we will talk about a couple of applications of BnB-PEP. There can be more, but for the interest of time, I will limit only in the two examples that I showed you briefly, and then I will conclude. First, let me start with the background. So what is the key problem in optimization? So optimization is all about solving this specific problem. We have some function f, which lies within some sort of function class, capital F. And what is a function class? It could be convex, non-convex, smooth, non-smooth, where we specify what are the properties of this function f. And the properties of those functions are encoded by this function class capital F. So x is our decision variable over which we are optimizing, and x lies in a d-dimensional space. Now, in practice, the problem dimension d can be very large, on the order of millions or billions even in large-scale optimization and machine learning. So the question is, what would be the fastest first-order method to solve this type of optimization problem? And we are interested in having dimension-independent guarantees too on their convergence rate. Now, let's talk about what is a first-order method. So very concisely, algorithms that can be described and analyzed with gradients or subgradients of the function f, which we are trying to minimize, are first-order methods. Now, if the function is differentiable, then we will denote it by this symbol nabla f. And if it is not differentiable, then we will denote it by f prime. But in generally, subgradient or gradient, broadly speaking, we will use the notation f prime. So the most classic example of a first-order method is the so-called subgradient descent, where, as you can see, that we have some previous iterate xi. And then we evaluate the subgradient of the function f at that previous iterate, which is f prime xi. And then with respect to some step size hi, we are going in the opposite direction of the subgradient. And this is how we are computing the new iterate xi plus 1, which is essentially xi minus the step size times the subgradient evaluated at previous iterate xi. Now, of course, there are many other first-order methods that we can design. So two more examples that I'm showing: Polyak's heavy-ball method and Nestorov's celebrated fast gradient method. Now, in both these cases, you can see essentially in terms of using the function information, it is only using the gradient or subgradient of the function. And of course, there are many other first-order methods that you can have, such as optimized gradient method, OGM, optimized gradient method for minimizing gradient of a smooth function, which is OGMG, item, which is the optimal method to in the strongly convex and smooth setup with respect to the performance measure of distance from the optimal solution. And we can design our own methods too. Now, of course, the question is why first-order method? Why are we focusing on this class? Because first-order methods, they're practically very relevant for machine learning and large-scale optimization problem. In fact, first-order methods, they have massively accelerated the machine learning training problems. Why this is so? Because their first-order methods, they're very cheap. They only require the gradient or subgradient information. And as a result, its computational cost per iteration is very low. It requires at most matrix vector multiplication. Not only that, first-order methods can be parallelized and scaled easily on multi-threaded CPUs, GPUs, and can be used with a lot of ease in distributed settings. Most popular deep learning methods, such as ADAM and so on, they are first-order methods themselves. So naturally, finding the optimal first-order methods to minimize a given function is of importance. And down the line, we are going to define the notion of optimality of an algorithm as an optimization problem itself. But prior to that, let's take a look at how a first-order method typically behaves. So usually, not all the time, but usually convergence rate of a first-order method with n iterations is usually of this form. So we have some positive number that is a constant divided by some n, which is the number of iteration, to the power some positive number. So it could be 1 over n squared, 1 over n, and so on. So if we plot that kind of convergence rate, it often looks like this that I am trying to show using my mouse. So for this type of convergence rate, a first order algorithm usually converges very fast in the beginning. So early phase of a first order algorithm is the best phase. And convergence tails as the iterations progress beyond a certain saturation point. So I am showing two examples. One is the first example that I illustrated at the very beginning for memory-free gradient method. And the other one is performance of gradient descent on training neural network. So you are seeing several curves because there are several training data sets. But even though the application context is very different, in this case, we are trying to minimize a convex function. Here, we are trying to minimize a non-convex function. We can see that qualitatively, both the convergence rate curves, they are behaving similarly. Like they're converging very fast in the beginning. There comes a saturation point, and even beyond that point is still getting better, but the rate of getting better is not as good as the beginning. Same goes for the neural network. There is a saturation phase, and beyond which it's kind of slowing down. So what do practitioners do in practice? So often what they would do, they will try to figure out where is this hypothetical saturation point, and then they will try to accelerate convergence by periodically restarting those first order methods. So here you are seeing the classic first order methods behavior on reducing the function value gap. So in practice, one thing practitioners often do is, let's say this is the saturation point, and at this point, they could potentially take an average of the previous iterates and then restart the algorithm again at this point in the hope that we will get the early phase behavior again and again. So in a practical sense, the early phase of the first order method would matter more. So if we have somehow the fastest first order method, in principle, we can repeat this best phase over and over, speaking from a practical point of view by restarting. And BnB-PEP actually can help us in finding that best phase of the fastest method. A very brief one slide evolution of first order optimization. Of course, it's a very broad and very classical field. I am just showing a very few of those landmarks. So it is a very classical field, first order optimization, and some of the early work we can trace back to work done by Cauchy. In the 1980s, many fundamental contributions in this field were made by Nestorov and Nemrovsky. Since the early 2002 present, they have become wildly popular and relevant due to large-scale machine learning. Now, the paper that I'm going to talk about, which is BnB-PEP. So this builds on top of something called PEP, which is performance estimation problem. And in my opinion, this is a new breakthrough in optimization. So I will briefly talk about what performance estimation problem is about. And this has led to many faster methods, such as OGM, OGMG, item, and so on. And where does BnB-PEP fits in this landscape? So BnB-PEP is trying to do a bit more. It's trying to find the fastest method. So now let's try to define what would be the optimal first order method, how we are going to define it mathematically. And then down the line, I will talk about what is PEP, performance estimation problem, and how BnB-PEP builds on top of that. So for our optimization variable, we are going to consider something called fixed step first order method. So consider the following first order method M with n iterates, which works as follows. First, we pick an initial point x0, which can be chosen randomly, because to start any algorithm, we need to start it with some initial point, right? Now, when we are trying to compute our first iterate x1, at this point, we have only one point, x0. So what we are going to do, we are going to compute, we have x0, so we evaluate the gradient or subgradient of f at the point x0. We have some step size at at our first iterate h1, and h10 corresponds to the step size associated with x0 at iteration number 1. So very briefly, what we are doing is computing the first iterate, x1 equal to x0 minus h10 f prime x0, because at this point we have only one subgradient or gradient. At the second iterate, x2, we have 2 points. We have x0 and x1. So we evaluate two subgradients, one at x0 and one at x1. And then x1 is our previous point, right? So the way we calculate it is x1 minus h20, which is the step size corresponding to f prime x0, multiply it with the corresponding subgradient, minus h21 analogous step size times the subgradient associated with x1. So at this point, we are seeing a pattern, right? So x3, we will move similarly. We have x2, so we take x2. We evaluate the previous 3 points that we have seen, their subgradient, f prime x0, f prime x1, f prime x2. And then we have the corresponding step sizes. So this process continues until we have reached the iteration number xn, right? So xn, how would it work? Based on the pattern, we see that it will be xn minus 1, the previous iterate, minus the sum of all the previous subgradients that we have seen up to this point times the corresponding step sizes. Finally, we return the point xn. Now note that we have not specified what those step sizes are. And this is the fixed step first order method, and this will be the class over which we will optimize. Now we will denote the class of all such methods by capital MN. So though it looks very generic at this point, the previous algorithms that I showed, for example of first order methods, subgradient descent, Nesterov accelerated method, Polyak-Savivol method, all lie in this capital MN. And you can actually see my blog where I show the equivalence between this canonical form versus these specific forms. So we can show that if a first order method has the so-called momentum form, that type of algorithm lies within this class. Same goes for Polyak-Savivol method and so on. Here I should note that I am calling this problem class fixed step first order method because these step sizes, they will only depend, in this case, the function parameters and the iteration number n. In other words, if we have an adaptive method, such as the so-called Fletcher-Reeves method, where the step size is ratio of gradient norm squared and so on, that will not fall within this fixed step first order method. However, for many relevant classes of problems, it turns out that capital MN, the class of fixed step first order methods, they are sufficiently large class to search for the optimal first order methods. So in the context of this work, we will limit our attention only to this class. And for adaptive methods and things like that, I want to clarify that this is not applicable. Again, for many setups, such as a strongly convex smooth setup, smooth non-convex setup, and so on, MN is often considered sufficiently large class to search for the optimal first order method. What does that mean? It means that there could be some optimal first order method outside this class, but MN is sufficiently large that you can find one optimal first order method with the same convergence rate within MN. Okay, so now that we have fixed what first order method class we are going to consider, the next question is how we are going to analyze the behavior of the method. So if we consider a method M in our capital MN, to analyze this performance, we will need 4 things: the function class F, starting point x0, some initial condition C, and a performance measure E. What is the function class F? So F, the capital F, which denotes the function class, it defines what are the properties of the function. So F can be a class of smooth convex function, class of non-smooth non-convex function, and so on. And I am going to give a rigorous definition of what kind of functions BnB-PEP can can deal with. We need a starting point because any algorithm needs a starting point x0 to initialize it. Then we need some sort of initial condition that relates the point x0 with one optimal point x star. Why we need that? Because that type of initial condition ensures that the initial point x0 is not infinitely bad. For example, we can define that notion of not being infinitely bad by saying that the distance from the optimal solution is finite, or the function value gap of the initial point with respect to the optimal point is also finite. So, but there can be other initial condition too, but their goal is ensuring that the initial point is not infinitely bad. Then one of the most important criterion is the performance measure. So this measures the performance of the method M on the function class. And common performance measure E could be, as we are giving more and more iteration, how the function value gap is improving. So this could be one performance measure. And if this is 0, then we have reached the optimal point. Okay, another performance measure could be how far we are from the optimal solution set. This is encoded by xn minus x star squared. Another performance measure could be, because this is a first order method, we are essentially trying to reach a stationary point where the gradient is 0. So one performance measure could be how the gradient norm squared of the last iterate is going to 0 as n is going up. Another performance measure could be that, okay, like minimum of all the previous gradient norm squared that I have seen in my n iterations and so on. Now, if M is working properly, and if we have chosen our performance measure carefully, then M should make the chosen performance measure go to 0 for every f in the function class. Because if it is working for certain functions and not for others, then it's actually not a working method. It should work for every function in the function class. Now, I told you earlier that I am going to clarify what kind of functions BnB-PEP can deal with. So here it is. So the BnB-PEP methodology applies to any quadratically representable function classes directly. So what does it mean? So a quadratically representable function f is completely described by inequalities of this form. That if we pick any 2 points x, y, and u, v are the corresponding subgradient, then the function class can be completely described by this inequality, where alpha and beta, they are scalars. So alpha fy greater than beta fx plus some quadratic function in x, y, u, v. Now, it turns out that most of the major, in fact, all the function classes in classic mathematical optimization that I know of, they can be fit in this quadratically representable function class. So here I am showing you the common function classes that are quadratically representable. So you can see that pretty much all the known function classes fit within this class. So I just wanted to show one example. If we consider strongly convex and smooth function, then we can, if we look carefully, then we will see that this is quadratically representable. We have alpha equal to 1, beta equal to 1, and then whatever I am showing here. So perhaps I can use my pen. So what I am showing here, this is actually a quadratic function in x, y, u, and v. Okay. So similarly, the other function classes too that I just showed, all of them we can show that they are quadratically representable. Now, another thing is that I am saying that the first order method, it only uses subgradient and gradient. So I need to make the notion of subdifferential precise too. What is a subgradient and what is a subdifferential? So this will be the notion that we are going to use in our paper and in this presentation. The abstract subdifferential of f, the function that we are trying to minimize at x, denoted by partial fx, is defined to satisfy the following properties, and any element of this set would be an abstract subgradient. So if we have a convex function, proper, closed, and convex, then the abstract subdifferential is just the classic convex subdifferential that we know about. If f is continuously differentiable, not necessarily convex, then its abstract subdifferential at x just contains the gradient. So it's only 1 point. The third property is if attains a local minimum at x, then the abstract subdifferential will contain the vector 0. So in other words, there will be an abstract subgradient that will be equal to 0 when you evaluate it at the locally optimal point. Finally, we have this this technical condition that for all y, which is a vector, and for all beta, which is a scalar, the abstract subdifferential is going to satisfy this property. So it turns out that pretty much all the different notion of non-convex subdifferential that we have, such as Clark's Rockefeller subdifferential, Mordukhovich subdifferential, and Frechet subdifferential are all instances of this abstract subdifferential. And one note here is that the notion of abstract subdifferential is due to Bauschke, Morsi, and Wang from this paper. Okay, so now let's try to make a summary of how we are going to analyze a given first order method and how we can, on top of that, define the optimal method. So if you want to summarize, then a good method M should make the worst case performance measure that we have chosen, should make it go to 0 as n increases subject to the initial condition. And now note that our worst case performance measure is with respect to all the functions f in the function class. Why? Because we want the method to work for all the functions. So the way we encode it by saying that it should even make the max of the performance measure over all the functions should go to 0. So naturally, how would we define the fastest optimal method M star? That should make the worst case performance measure, the maximum of the performance measure E over all the functions in the function class F, go to 0 at the fastest rate as n is increasing subject to the initial condition. One example, suppose we pick our function class to be the class of strongly convex and smooth function. We pick our performance measure to be how the last iterate gradient norm square is going down, and our initial condition is distance from the initial distance between the initial point and the optimal solution, which is less than equal to r square, which in other words saying that is not infinite distance away from the optimal solution. So the fastest method M star should make the maximum of the last iterate gradient norm squared over all the function f in f mu will go to 0 as fast as possible as n is increasing subject to our initial condition. So down the line, we will construct the optimal method for this setup as an illustration. So what I just said right now, if we want to write it as a meta-optimization problem, we can do that as follows. So if we know the method M in Mn, then its performance measure on the function class f is defined as follows. That we are trying to find the worst case performance measure, right? So like how the method will behave on all the functions in that function class. So that's why we are trying to maximize. This is the performance measure. Again, like it could be gradient norm squared over the last iterate and so on. What are our decision variables? One decision variable is it needs to be done over all the function f in the function class. We are also trying to figure out the worst case behavior of the algorithm. So that's why the algorithm, the points generated by the algorithms itself is part of our decision variable set. So this is where we are saying that x1 to xn generated by m from the initial point x0. We need to encode that x0 is not infinitely bad compared to x star. And of course, we need to compare it with something, right? Which is the globally optimal solution x star to the optimization problem that we are interested in solving. Now, performance estimation problem, PEP, shows that for a known M, this inner problem, so we are calling this entire problem or inner, we can show that, or using PEP, we can show that this O inner can be solved as a convex semi-definite optimization problem. Now, if we don't know the method and if we are interested in finding the optimal method, what do we do? We will take this inner problem inside, right? And then we are trying to find the method that will make the worst case performance measure. It will find the minimum of that, right? So essentially, we are trying to find the min max. So inside we have this worst case performance measure, and on the outside we are trying to minimize that worst case performance measure over all the methods in our fixed step first order method class. And BnB-PEP shows that this outer problem that we have can be solved as a non-convex but practically tractable QCQP. QCQP means quadratically constrained quadratic optimization problem. Okay, so this is the problem that we will focus on. But again, note that the inner problem, we are saying that the inner problem can be solved for a known algorithm as an SDP. So I need to do I need to do a very brief literature review of PEP-based work. Of course, this is not exhaustive. So I apologize if I have missed any work on PEP, but here I am mostly trying to focus on those works that try to discover efficient methods based on PEP. So the field of PEP was actually started by Yoel Rory and Mark Tabule in 2014 in this seminal math programming paper. And after that, over the years, there have been a few works that try to discover better methods using PEP methodology. Among those notable works are the work by Kim and Fessler, where they found an analytical solution of OGM that was proposed numerically by Drury and Tabule. Then there has been few works in the integral quadratic control community, which also uses computer-assisted proofs to discover better methods. So these two are representative of IQC. Taylor and Buck, they used a potential function-based setup to discover proofs and find non-asymptotic convergence rate. Drury and Taylor, then they used certain span search based procedure to discover efficient first order methods in convex optimization. Then in 2021, last year, there were 3 papers that discovered better algorithms using PEP-based methodology. Here are those 3 papers. Now, even though those papers that led to faster algorithms, it has some limitations when you are only relying on semi-definite programming-based approach. Now, PEP, if you know the algorithm, then the classic performance estimation problem will formulate the inner problem tractably as a convex SDP. However, if we want to solve the outer problem as an SDP, then it's often not possible and successful applications limited to only a handful of setups. In some cases, alternating minimization-based approach can give us better algorithms, but without any certificate of optimality. Then in many of those applications, we need to relax the set of interpolation constraints, the constraints that define the function properties. We need to relax or drop them in advance to come up with a tractable formulation or relaxation, I should say. But it is not always clear which ones to drop. And it does not work very well when F is not convex. So the SDP-based approach, if we are interested in finding a better algorithm or even the optimal algorithm, has many limitations. So what does BnB-PEP do? So BnB-PEP actually does not try to form outer optimization problem or outer as a SDP. It tries to formulate it as a non-convex but practically tractable QCQP. And by confronting the non-convexity directly, it offers significantly more flexibility and removes the many limitations of the SDP-based approach. As I told earlier, it proposes a customized spatial branch and bound algorithm to solve those QCQPs to certifiable global optimality in a practical timescale. And empirically, we show that because our algorithm exploits the problem structure, our algorithm on a laptop outperforms the default Gurobi, which we can use to solve this type of optimization problems, running on MIT SuperCloud by orders of magnitude. So I will show one small example where I am trying to show that how the optimal algorithm is being calculated in a certain setup. And as you can show, I am comparing the runtime of BnB-PEP algorithm, our algorithm running on a laptop, and the default group where we are not exploiting any structure, we are running it on MIT SuperCloud. And as you can see, as n becomes 4 iterations, like it's just impossible to use the default spatial branch and bound algorithm, because at n equal to 4, you are requiring more than a week on MIT SuperCloud. And here I am trying to show the resource difference between my laptop and MIT SuperCloud. So as you can see, even if we give Gurobi all the resources in the world, if you don't exploit structure, it's not going to work well. Now, of course, this is not any criticism of Gurobi. It is because in the end, like when we are constructing our customized spatial branch and bound algorithm, we are using Gurobi like in certain places as our base spatial branch and bound solver. But we are also trying to ensure that we exploit all the structures. So this, in a way, shows that if we are willing to exploit structure, what a difference it can make. So now let's go into how BnB-PEP works. So it has two phases, the formulation phase and the solution phase. Let's start with the formulation phase. So as an illustrative example, I will consider minimizing a function fx, which is strongly convex and smooth. So what does it mean, mu strongly convex? It means that it is so convex that if I take away a certain quadratic term from it, it's still convex. And L smooth means that its gradient is Lipschitz continuous. Now, we want to find the fastest first order method to reduce the gradient norm squared. So the gradient norm squared is our performance measure, and it's going to be gradient norm square of the last iterate. Because we are running like hypothetically, we are trying to solve it on a large machine learning problem or a large scale optimization setup, we will assume that the problem dimension D is much, much larger than the number of iterations we are going to run. Okay, so what is going to be our generic first order method M, the so-called fixed step first order method? We will write it in this format: xi equal to xi minus 1 minus 1 over L, which is the smoothness parameters, times the sum of all the previous gradients at the previous iterates, and hij tilde, which is our step size. So I am writing it in this format, and I am scaling it by the smoothness parameter L, because if I write it in this format, then I could just solve for L equal to 1, and this will give me the optimal step size for other L's as well by scaling, by dividing whatever step size I get by L. So now note that M is completely parameterized by the step size H tilde, and by H tilde, I mean the list of all the step sizes. So the optimal method M star in this setup will be a solution to the following min-max problem. So in the inner problem, I have the worst case performance measure subject to the different constraints. And the outer problem is trying to minimize that worst case performance measure. Now note that because this is a first order method without any loss of generality, we can translate our optimal point x star to 0, and we can assume without loss of generality that the optimal function value at the optimal point is also 0. Now, at this point, solving this problem is not so easy, because f, which is a function, is an infinite dimensional decision variable. So this optimization problem, or outer, is an infinite dimensional optimization problem. Now, during the formulation phase, we will convert this into a finite dimensional problem. And to that goal, we will first work with the inner optimization problem, and we will turn the inner infinite dimensional maximization problem into a finite dimensional minimization problem. So now let's see how to do that. And while in this process of converting the inner problem into something finite dimensional, for a certain point, we will, until a certain point, we are going to use the classic PEP, and then we will diverge. So now let's see how from how to go from the infinite dimensional inner max problem or inner to a finite dimensional inner maximization problem. So let's just go back a couple of slides. So this is the inner optimization problem. So I am just going to work on the inner optimization problem first. So at this point, I am just looking at the inner problem, which is a maximization problem, right? And then I have my outer problem when I do the minimization with respect to h tilde. Now, with respect to the inner problem, note that h tilde is not a decision variable. So in a way, is being taken care of the outer problem. So with respect to the inner problem, h tilde is fixed. Okay, so at this point is intractable. So the first thing that I am going to do is a very simple reparameterization. So I have my function f in strongly convex and smooth, and I will turn it into by a variable translation. I will work with f tilde, which is a smooth optimization problem. So what does it mean? It means that I will define a shifted function f tilde, which is equal to fy minus mu over 2 y minus x squared, and rewrite the previous problem once I have defined this f tilde in terms of f tilde. Now, while this shift is not necessary, if we do this shift under variable translation, like it is the same, like the optimization problems in a way they're equivalent, and it will make the final optimization problem smaller in terms of number of non-convex terms. Okay, so now what is the property of this f tilde? So f tilde is L minus mu smooth if and only if f is mu strongly convex and L smooth. One property that we are going to use that if we define f tilde this way, then the minimizer of the previous function and the minimizer of this new function f tilde will be the same. Another interesting thing is that by introducing a new step size alpha, we can write m acting on f, which was this optimization problem, we can write in the following format where m is acting on f tilde. So the benefit of working with this form is that it's working on the new decision variable, right? The previous one contains f, and in the new new formulation, we want to get rid of f. Now, so like down the line, we are going to optimize our alpha and not h tilde. The good news is that if we compute the optimal alpha, then we can recover what would be the optimal h tilde for the original function f by solving the following triangular system of linear equations. In other words, solving over alpha does not cause any issue. Okay, so we had the infinite dimensional inner maximization problem. We apply the reparameterization, and we have this shifted infinite dimensional inner maximization problem. Now note that at this point, everything has been written down in terms of f tilde, and our new optimization variable with respect to the outer optimization will be alpha now. Okay, so what to do next? First, we note that we have this constraint that this f tilde is written very abstractly. We are saying that it's L minus mu smooth on RD. Now, how to encode this mathematically? So we need to characterize this function class, how to say this mathematically. So f tilde is L minus mu smooth on RD. What it means? It means that for all xy in RD, it is going to satisfy this following inequality. And in fact, it turns out this f tilde, which is L minus mu smooth function class, is completely characterized by this. So this is if and only if. Okay, so once we have applied this, we have this compact infinite dimensional inner max problem. But things actually have not gotten any better. It's still infinite dimensional. It's just we are using a mathematical definition of the function class f tilde. So what to do next? After this, we are going to use a very important concept in performance estimation literature, which is interpolation. So using this interpolation, we are going to convert this infinite dimensional inner max problem into a finite dimensional inner max problem, though it will be intractable. But this is a very important step. So what does this interpolation argument say? Now, first, we define index set of all the points seen by our method M as IN star. So these are the index of all the points that our algorithm is going to encounter in the previous optimization problem. So if we look at it carefully, we will see that this algorithm is only experiencing the function f tilde at point x0, x1 until xn, and it also needs to know how the algorithm is behaving, how the subgradient f tilde is behaving at x star. In other words, the function f tilde, even though it's infinite dimensional, our method M is seeing the function f tilde only at those points. So xi, I in in star, it means that it is only seeing, evaluating the function at those points, x0, x1 until xn, and then x star. So the method is seeing the function only at a finite number of points and needs only the function values and gradients at those points to describe the optimization problem. Now, a very big step in performance estimation literature is the following result by Adrian Taylor and his co-authors. He showed that without any loss, the infinite dimensional constraint, the one that appeared in the previous optimization problem, can be replaced with the finite number of constraints written as follows. So which are those finite number of points? So these are exactly the points that are being experienced by the algorithm or our method in the course of running the first order method. Now, naturally, you can see that one direction is obvious. Like, of course, if the function f tilde is satisfying this property, this implies that this discrete set of inequalities, which is in a way a discretization of this inequality at the points that the algorithm or method is experiencing. So in a way, it's obvious, right? That like those discrete set of inequalities will hold. What Taylor and his co-author showed is that if we have the discrete points, like if we have the discrete points where we are evaluating the function, the gradient, and the points themselves, then from that we can actually go backwards and construct a L minus mu smooth function. So it is true in the opposite direction as well, and this was a major result. So this type of function class where both direction is equivalent, you can go from continuous inequality to discretized inequalities and backwards. So this type of function classes, they are called interpolable function class. And strongly convex and smooth functions, they lie within this function class. So in other words, even though we are doing this discretization, there will not be any loss in terms of the relaxation in a way is tight. Okay. So at this point, by using the interpolation argument, we have turned that infinite dimensional problem in a finite dimensional problem, because now we don't have infinite number of constraints of this form. In fact, we have like finite number of them. Now here, for convenience, I am using this notation that by GI, I mean the gradient of f tilde evaluated at xi, and fi means the function value of f tilde evaluated at xi. So at this point, we have a discrete problem, and we have a like finite dimensional problem, sorry, but it is intractable. Why? The main reason is in this setup, our xi and gi, they are lying in this very high dimensional space Rd. So if we want to encode it in this format, it's not tractable. However, one key observation in performance estimation literature is that in this formulation, if we look very carefully, we will see that xi and gi, they do not appear by themselves. They only appear in terms of inner products and norms involving this gi and xi term. So if we look carefully, we will see that this is an inner product of gj with xi minus xj. This is also an inner product, right? Because norm is inner product with itself. This is also an inner product. This is a norm squared. This is a norm squared. So whenever we are seeing that like x naught and so on, they're appearing in a way, they are always appearing in terms of inner product and norm squared. There is one part where it is appearing as xi minus x naught and so on. But if we replace this value of xi there, we will see that the entire problem can be written in terms of inner product and norm. Now again, note that I wanted to reiterate that even though we have this xi equal to this, we can just take this and replace the value of xi in those points where it appears. And then the only thing that we will have after that replacement is inner product and norms involving GIs and XIs. Okay. Now, what to do after that? After that, we will use something called Gramian transformation. And by doing that, we will turn this problem into a rank 1 semi-definite optimization problem in maximization format. What it means is that we are just going to introduce new variables so that we can cleverly write the inner product and norm squared as trace of some decision variable with some constant. Now, how does that work? So if we look carefully, this is what is going on. So we are defining 3 new variables. First, we define P, which kind of stacks x naught, which is the first point. Then it is containing the gradients seen by the algorithm. And then we are defining G equal to P transpose P. Finally, we are defining this matrix F, which contains all the function values. Now, why we are doing it? The reason of doing this is that once we have defined these new variables, then the main goal is by multiplying these matrices with some input vector, which are constant in a way for a fixed alpha, we can completely reproduce our original variables xi, gi, and fi. So in other words, if we define these 3 matrices P, G, and F, then there will be some constant vector with respect to known step size, such that upon multiplication, we can reconstruct our original decision variable small xi, gi, and fi. More specifically, we can define a few bold vectors. So I am showing you here. Most of them, they are actually constants. So you see that this bold G star is equal to 0. And this has this property that if I multiply this G star with P, I will get G star, which is actually 0 at the optimal point. Then GI, if I define GI as follows, where E is a vector with only one non-zero entry, which is 1, at I plus 2th position and is 0 everywhere. So in other words, EI plus 2 means that is 0, 0 everywhere at the I plus 2th position. It is 1 and rest is 0 again. So this is EI plus 2. If we have that, and if we multiply this with this matrix P, then we will get back our original small gi. Similarly, it goes for this bold x naught, x star, and so on. One thing to note is that for a known alpha, this xi alpha, if I define it as follows with respect to these bold vectors, bold x naught, and alpha is again our step size. But for a known step size, this is also a constant vector, right? And if we multiply xi alpha with p, then we will get back our original points generated by the algorithm. Finally, we have the function values defined as follows: f star equal to 0 and fi equal to ei plus 1. And this is going to satisfy this property that small fi, which is the function value, will be equal to f times this bold fi. So once we have done that, there is a major advantage, is that defining symmetric outer product. My apologies if this is getting a bit technical, but this is actually important. And one thing that you could do is just trust me that, okay, like this is correct. But I will try to go through what is actually going on. So if we define symmetric outer product, as follows, which is a symmetric matrix. Then I can define this new parameterized decision variables aij, bij, cij, and aij, such that all the inner products and norm square that appeared in my previous formulation, they can be written down as trace of the matrix G that I defined here times aij alpha. Xi minus xj squared would be written down trace of G and bij alpha, and gi minus gj squared can be written as trace of G times Cij. Now, for a given alpha, this is going to be linear, completely linear in G and B. Now, of course, when we are trying to optimize over alpha, certain things will happen, and we need to, which actually going to make the final problem non-convex. Note that aij alpha, if we don't know alpha, so then it's linear in alpha, and bij alpha, it is actually quadratic. Because if we look carefully, this is subtraction of xi minus xj, and xi alpha is linear in alpha. So when we are doing the symmetric outer product, it is becoming quadratic. Okay. So once we have done this, we have this intractable finite dimensional inner maximization problem. We apply this Gramian transformation. And then we have this another optimization problem, which is equivalent because we did not lose anything during this transformation. We have actually method of going back to our previous problem. In this setup, we have this decision variable G and F. And for a known alpha, it's an SDP. Everything is fine. Note that like G, this is linear in G for a known alpha. This is also same, it's a convex constraint. G is positive semi-definite. This is a convex constraint. This is again a convex constraint. The only downside is we have this rank constraint, which is non-convex, and we are saying that rank of G will be less than equal to D. Now, this is where the large scale assumption saves us, because we are assuming that our dimension D, problem dimension D, is much larger than the number of iteration we are going to give. Now, if we assume that D is greater than n plus 2, because G itself is a n plus 2 by n plus 2 matrix, so then rank of G will be less than equal to n plus 2, and rank of G less than equal to D will be satisfied automatically. So in the large scale setting, because D is much larger than n, this is a reasonable assumption. So in this setup, rank of G less than D will be automatically satisfied. And then we can just drop it. So once we do that under that large scale setting, we have this so-called convex maximization SDP. And everything is very nice as long as we know the step size where alpha is fixed. So here what I'm going to do next, I'm going to take dual. So that's why I am trying to show the dual multipliers, lambda, ij, z, nu, and so on. So what it means is that so this is my constraint, consider this constraint. And then corresponding to these constraints, I have this dual variable, lambda ij, which is going to be positive. Similar, we have this minus G will be a negative semi-definite matrix. So the dual multiplier corresponding to this is Z is greater than 0. And finally, this is the initial condition in the new format, which has the dual multiplier nu greater than equal to 0. So at this point, I'm going to take the dual. So because this is a convex optimization problem, we can apply this thumb rule that strong duality usually holds for convex optimization problem and so on. But there is a precise rule in this setup too, that strong duality will hold as long as M is using the gradient of the last iterate. In other words, at iterate xi, if M is using the gradient of f tilde at xi minus 1, which is a reasonable assumption. So if we have the precise rule holding, then strong duality will hold. And after I take the dual, there will be no loss. So this is how the dual looks like. So note that in the new optimization problem, my decision variables are lambda, nu, and z, which were the dual variables corresponding to different constraints in the primal problem. Now, because in the context of BnB-PEP, they are going to play an important role, a very important role in the context of finding proofs. So we give them this name that which we say that these variables lambda, nu, z, they're inner dual problems. It means that they're the dual variables of the inner problem. What is interesting is that it is a convex SDP for a non-M, right? So if we know the method, then alpha is known, and then everything is convex, and this is a convex SDP and reasonably easy to solve. Now, this is where the classic PEP ends. And from now, we will diverge. Now, our goal is not so much in analyzing the performance for a non-M. Our goal is finding the best M, right? So to that goal, we actually do something like non-obvious. We will turn this convex problem into a non-convex problem. Why? Because if we do so, down the line, the final problem that we want to solve, which is outer or outer, that will become an easier problem to solve. Okay. So to that goal, we are going to use the Cholesky decomposition. So a matrix Z is positive semi-definite if and only if it has a Cholesky factorization Z equal to PP transpose, where P is lower triangular with non-negative diagonals. So if we want to say that, like in terms of constraints, that P is lower triangular with non-negative entries and PP transpose equal to Z, we can write them in terms of these three sets of constraints. Now note that the first two, they are linear constraints in P, but the final one is actually a set of bilinear constraints. Another thing to keep in mind is that this P corresponds to a new P. It's not the same P that we introduced earlier. So P in a way is like overloaded. Please keep in mind this P corresponds to the Cholesky decomposition of Z. So this is not the same P I introduced a few slides ago. So if I go back, so there was this P that I introduced. So the new P that I am saying that Z equal to PP transpose, this is an overloaded P. So the new P that will appear our final formulation that corresponds to the Cholesky decomposition of the dual slack matrix Z. Which is fine because the initial P that we said, it actually does not appear at this point, like when I am imposing this new overloaded P, so everything is fine. Okay, so once we have done this Cholesky factorization on this convex minimization SDP, after that, this actually, the inner problem becomes a non-convex QCQP in minimization form. Why? Is because of just this last two sets of constraints. That P is lower triangular with non-negative diagonals. This is linear and fine, but Z equal to PP transpose, this is a non-convex constraint. Okay, so if we summarize, so we did a lot of transformation. So I wanted to summarize what actually happened. So we have this infinite dimensional inner maximization problem E inner, and what is the current state of the finite dimensional inner maximization problem. So this was our initial problem, the infinite dimensional inner maximization problem. And after a lot of transformation, we converted it into a non-convex minimization QCQP, which you see at the bottom. Now at this point, our interest is converting the O outer, right? And we want to convert it into a format that we can solve. So we are going to convert the O outer to a non-convex QCQP. Now remember, this was the original min-max problem. So we were doing this minimization with respect to H tilde, and this was our inner problem, right? So we have converted this inner problem into a non-convex QCQP. So let's put it there and in minimization form. So once we have done that, we can write down the entire problem as one minimization problem. One thing to note is that the step size is alpha. Keep in mind that once we have alpha, we can find H tilde, our original step sizes, by solving a linear system. So if we look at it carefully, we will see that this is a non-convex QCQP. Why? Because this specific term has this Bn star alpha. This is quadratic in alpha. This Aij alpha, this is linear, but then we are multiplying it with lambda ij, which is another decision variable. So this is becoming bilinear. PP transpose equal to Z. This is also quadratic in the entries of D. So P. So in the end, this is a non-convex QCQP because these are also equality constraints. So that's why this is a non-convex QCQP. So now the question is, even though I showed one example, so it turns out that the basic recipe of the BnB-PEP QCQP formulation is basically the same for other setups as well. Other performance measure, other function class, and so on. So it turns out we will go through the same set of transformation that I just showed. And in the end, we will end up with this so-called BnB-PEP QCQP. So why do I give it a specific name? Because it turns out that they almost always look very similar. So in the general case, though the details might vary, but roughly the structure would be of this form, and this would also be a non-convex QCQP. So broadly speaking, we say that all these QCQPs, because they share so much structure, we call them BnB-PEP QCQP. Now, one question at this point regarding the formulation could be that why not solve the problem as a bilinear matrix inequality? Now, even though that is a reasonable path to take, now it turns out at the existing state-of-the-art BMI solvers, they are not numerically very stable, and they do not allow for callback features that can customize the solution process, which we use heavily in our solution algorithm. Another thing is that the local optimality theory for BMI solvers, they are not as good compared to a non-convex QCQP. Not only that, just to give a brief summary of what is the state of the art for this type of solvers, is the only commercial solver that I know of is the so-called PEN BMI solver that can deal with BMIs. However, there are two things. One thing is that like it has not been updated since 2014, the last time I checked. And it also states in these two papers very clearly that the algorithm that they're using in PEN BMI, they are not necessarily work in a reliable way for non-convex problems. And this is exactly how they work in practice too. So as a result, we don't take the BMI route because we found it almost impossible to find even a locally optimal solution, let alone a globally optimal solution. So now let's talk about how BnB-PEP works in terms of the solution phase. So we have done the formulation. For a specific example, we argued that in the end, it's like all for other setups too, is going to look structurally the same, hence the name BnB-PEP QCQP. So now let's discuss how BnB-PEP will work in terms of solving the BnB-PEP QCQPs. So to that goal, we propose the BnB-PEP algorithm and its implementation. You can find it in our Julia code that is open source. So it is a three-stage algorithm. Stage one, it will find a feasible solution by solving a convex STP. Now, for all the relevant function classes, we have recognized a list of feasible algorithms that can be used to find such a feasible solution. What the stage two is going to do, stage two is going to warm start with the solution from stage one, and then it will find a locally optimal solution using nonlinear interior point algorithm. So in terms of their convergence rate, and the theoretical result is that if we warm start at a good enough point, a point that is not too far from a locally optimal solution, then such algorithm will give you a locally optimal solution at a quadratic convergence rate under certain regularity conditions. Empirically, we find that under good warm starting, it almost always finds the stage two itself finds us a near optimal or optimal solution in many cases. By near optimal, I mean in terms of the optimality gap, the relative optimality gap, it's often between 0 to 5%. So even at the stage two, we are able to discover a better algorithm compared to the stage 1 solution. Stage 3 solution, it would take the stage 2 solution. Okay, so this is a typo. So this should be stage 2. So the locally optimal solution that we find in stage 2, we will warm start our customized spatial branch and bound algorithm with the stage 2 locally optimal solution, and then we will find a globally optimal solution. Okay. So let's talk a little bit about the customized spatial branch and bound algorithm. So compared to the default Gurobi algorithm or any default spatial branch and bound algorithm that does not know any problem structure, in a customized spatial branch and bound algorithm, we provide the problem-specific insights to the default branch and bound algorithm by the callback features. So how will we do that? There are other things that we have done, but these are the main 4 customizations that we have done. First, we compute a tighter valid bounds on the variables. We find an improved lower bound on the objective value. We implement custom heuristics at each node of the branch and bound tree, and we also find the sparsity pattern of the inner dual variables. So let's talk about the first one, where we are computing tighter valid bounds on the variables. Now, we have a QCQP, but we can construct a rank 1 semi-definite relaxation of the BnB-PEP QCQP itself, which is a relaxation. And we have bound on the objective value from the first 2 stages of the BnB-PEP algorithm. The lower bound is always 0, and the upper bound is corresponding to that of the feasible solution that we find in stage 1. So using that, we can construct and tighten bounds on the variables from the SDP relaxation, because any bound that we find on the variables from a relaxation would be also valid bounds for the QCQP2. Then we can also construct implied bounds from exploiting the structure of the BnB-PEP QCQP. So when we use all those bounds in the spatial branch and bound algorithm that the default algorithm would not be capable of computing, that will reduce the search space of the spatial branch and bound algorithm significantly, and this will lead to major speed up. Then we find an improved lower bound. So keep in mind, a default lower bound is 0 because the performance measure is always a non-negative quantity. Now, to compute an improved lower bound, we can replace some of the quadratic constraints, the constraints that are causing the non-convexity, hence the hardness of the problem. We can replace some of those quadratic constraints with valid linear lazy constraints. So what is a lazy constraint? So a lazy constraints are type of constraints that are not generated upfront in the optimization model, but they are generated and added one by one when needed. So one very simple example of lazy constraints is the so-called Cholesky constraint that we introduced, which made our problem, the inner problem, non-convex, right? So because this is a positive semi-definite constraint, we can replace it by a finite number of constraints, which would be a relaxation, because any positive semi-definite matrix for any matrix V is going to satisfy V transpose ZV equal to greater than equal to 0, but it will be for infinite number of V's. So what we do, we take this and we replace it by a finite number of them. Hence, it makes it a relaxation. So it's a simpler QCQP, right? Because many of the problematic non-convex constraints, they go away. But it's a relaxation. So we solve that and solve our the relaxation of the BnB-PEP QCQP. And after that, we find the corresponding Z. Now, if that Z is positive semi-definite, then we are already done and we have found a globally optimal solution. Now, in many cases, this is not the case. So what we do, we find the most negative eigenvector V tilde, which kind of is violating that V transpose V greater than equal to 0. And then to cut off that specific like constraint, we add this lazy constraint. Cut off that point, we add this lazy constraint, V transpose V tilde is greater than equal to 0. So we have added only one linear constraint. And as a result, at the node of the branch and bound tree, using dual simplex, we can compute the new solution corresponding to just this constraint very easily without not spending too much time in new iterations. So This process will continue until a max number of lazy constraints have been reached. In our example, the total number of lazy constraints we add, I think, is 10 to the power 6. Now, because the cost of adding these lazy constraints is very small, this in the end ends up becoming a much faster process compared to if we had the entire z equal to pp transpose thing. So having this improved lower bound, so we compute that improved lower bound. Often it is already very close to the upper bound. Thus, when we are starting our spatial branch and bound with that improved lower bound, our search space is already very small, and the algorithm ends up converging much faster compared to the case if we did not provide an improved lower bound. Okay, so the other thing that we do is that we implement a custom heuristic at each node of the branch and boundary. So it exploits the fact that for a given step size vector, generating a feasible solution of the BnB-PEP QCQP is a convex problem, right? It's a convex STP. So what we can do, we can potentially query the current solution at each node of the BnB tree once our optimality gap is small enough, and then take the step size vector rather than our spatial branch and bound algorithm finding the other solutions, right? Like the other decision variables such as z, p, and so on. We could just compute them by solving a convex SDP and provide that solution directly at the node of the branch and boundary by custom heuristics. So we can do this by the so-called callback function. So if we do that, of course, in many cases, it can speed up the solution. However, in practice, we have noticed that because our stage 2 solution is already pretty close to the optimal solution, having that does not speed up the algorithm significantly. That being said, in certain cases, if it turns out that finding a locally optimal solution is hard, this can provide significant speed up. Finally, once we have found, so using all those three callback features, finding valid bounds on the decision variables, finding an improved lower bound, and using the custom heuristic, when we start our algorithm, it actually ends up finishing much faster than just a default Gurobi algorithm. One additional thing that we do, we also find the sparsity pattern of the inner dual variables, lambda, by L1 norm minimization. Why we do that is the sparser the inner dual variable, simpler would be the proof when we are trying to find a proof. So this is why after we find the optimal solution, we also find the sparsest optimal solution by L1 norm and trace minimization. So L1 norm minimization for the vector valued decision variable and trace for the dual slack matrix Z. So we do both things, L1 norm minimization plus trace minimization over that optimal sublevel set. So what is a potential application of doing this is that by imposing this sparsity pattern in the support of the optimal lambda star, we can recognize which interpolation constraints can be dropped. So keep in mind in traditional PEP, when we are trying to find a better algorithm, often we will start with a relaxed set of constraints, which tend to differ from one setup to another. So this actually gives us a principled way of recognizing which interpolation constraints can be dropped without hurting optimality. Not only that, another benefit of having this polishing is that if we can recognize the sparsity pattern, then we can impose that sparsity pattern for larger n. That will lead to smaller BnB-PEP QCQP, and this will lead to faster runtime. Now, of course, imposing this sparsity pattern for larger n will make this inherent assumption that what the pattern that you see for smaller values of n will hold. But empirically, we have actually found this to be true. So from a practitioner's point of view, this is actually a good idea to speed up the runtime. Okay, so this shows the runtime, and I actually showed a summarized version of this runtime table before. So I will skip this. This shows the kind of results BnB-PEP will generate. So this is for L equal to 1. So if we are interested in some other L, then the corresponding step size actually will be 1.3837 over L for iteration number 1, and so on. So you will divide these step sizes by L. So as you can see, the optimal algorithm actually changes given the number of iterations that we are interested. The number of iterations, like if it changes, the optimal algorithm is going to change. So in this case, also like this experiment was done with L equal to 1 and mu equal to 0.1. This shows the convergence rate of BnB-PEP algorithms with popularly known algorithms. And as you can see, BnB-PEP is actually doing better with respect to item and OGM FMU. So how do you know that it's doing better? Because the way it's reducing the performance measure is actually smaller than the other algorithms that we are comparing it with. How to read this table? We can read this table as follows. Like, so these are shown for L equal to 1, right? But by using a scaling argument, we can convert these convergence results for other L's too. Like for example, for fifth iteration, this basically means the last row and this column means that the worst case performance measure of the optimal algorithm after 5 iteration is going to be less than equal to 0.002459 times L square R square, where R is the distance from the optimal solution at the initial point. So I wanted to talk about some empirical observations that I have noticed. One is that if we are interested in finding just a better algorithm compared to some known algorithm, this is my experience that only the first 2 stages of BnB-PEP algorithm, they give near optimal solution or near optimal first order method. Optimality gap often is actually 0 in many cases where it's not. In many cases where it's not, it is actually within 0 to 5%. Now, the first 2 stages of BnB-PEP algorithm, they are very fast. They are almost real time for n less than equal to 25. If we are interested in computing n up to 100, that can be done within 2-3 hours. And one thing is that the convergence guarantee of the constructed algorithm can also be verified by Pesto, Pepit, and so on. Now, the full BnB-PEP algorithm is implementing a customized branch and bound algorithm. So that takes longer. Now, if we are interested in solving those problems, then what we can do for the third stage at this point, in a way, it takes longer compared to the first 2 stages. So if we are interested in n up to 10, that can be done within 2-3 hours. N up to 50 with a certifiable optimality gap of 10% can be done within a day. So of course, I'm talking about a very generic laptop. The more resource we can spend, faster it would be. And if terminated early, the algorithm has this benefit that it will provide a certifiable optimality gap and also a global upper bound, which is helpful because whatever algorithm we know that the optimality gap tells us how far it is in terms of the relative optimality gap from that absolute optimal algorithm. Okay, so now I will start some applications. So I will give 2 applications. One is constructing the best gradient method without memory for a smooth convex minimization. And then I will talk about generating convergence proofs for non-smooth, non-convex minimization. For other applications, please take a look at the paper. So best gradient method without memory. First, let's try to understand what problem we are trying to address. Suppose we are trying to minimize a smooth convex function. So there is a typo here. There should be x in RD, where f is L smooth convex. We want to consider memory-less gradient descent. In other words, this type of gradient descent, unlike Nestero's method, does not have any momentum term, or it doesn't have any memory. It's only looking at the previous gradient, and that's it. We are considering the performance measure in terms of the function value gap of the last iterate. Now, a reasonable and interesting question is, what is the best gradient method without memory? And in a way, this is one of the first problems that you can ask in optimization, because the simple gradient descent is often presented as the very first order algorithm in optimization classes. So prior belief was that the best algorithm is going to satisfy, it will be within this interval of 0 and 2 over L. Now, once we apply BnB-PEP to this setup, we see some very interesting things. So if I am plotting the worst case performance measure of different algorithms in log-log plot, so this is the step size of 1 over L, for which we have a convergence proof of rate O of 1 over N. So the blue curve corresponds to that. This is for the step size proposed by Taylor et al. So this is in the paper shown here. And finally, the red curve corresponds to BnB-PEP. So as you can see, the BnB-PEP algorithm in log-log plot, we see that, okay, it clearly corresponds to a different rate, and it is actually somewhat faster than 1 over N based on these 50 iterations that I have plotted. So one thing that we can do from this log-log plot, we can actually find out what would be the best fit in terms of rate. And it shows that it is actually, the rate is corresponds to some constant by n to the power 1.178. So the previous or even still now, the best theoretical rate that you can prove is O1 over n. And this is faster than that. But it is slower than Nestero's method, which is O1 over n squared. And here I am showing the fit in the regular scale. And as you can see, this is a pretty good fit. So another surprise is naturally is that the step size. So the step size in a normalized fashion, it clearly turns out to be much, much larger than 2 for n equal to 5, n equal to 10, n equal to 25, n equal to 50. And no matter what n we are solving it over, we have found it that the optimal step size is greater than 2 over L, which kind of goes against the belief that the optimal step size has to be between 0 and 2 when we are considering a scale step size of h over L. In fact, when we go to n equal to 50, we see that, okay, there is one very long step size in all the cases. Now, naturally, one question is that, okay, how do I know that there is no bug in the code? Maybe somehow the step sizes are wrong. Well, if we can actually take these step sizes, which is available at the code website at GitHub, and we can feed it into Pesto or Pepit. And you will see that they are actually leading to curves that corresponds to what I have shown here. So even if you question the optimality or validity of the code and whatnot, the rate that we are finding, they are actually leading to much faster, not much faster, but is clearly faster than 1 over n if we focus in a finite number of iterations. Okay, so even though it is surprising, one question that one could ask is that, okay, like what is the analytical step size? Is there any analytical pattern and so on? Based on our current investigation so far, we were not able to see any pattern in terms of providing a closed form solution for these optimal step sizes. So one question can be, and to be very honest, of course, these step sizes, they correspond to root of some very complicated polynomials. However, they don't seem to have sufficient patterns that if I go from n equal to 50 to n equal to 51, the polynomials change significantly. So one question immediately is that, okay, like these are numerical step sizes. What can you prove, and what can you what would be the best analytical step sizes in certain setup? So this is what I am going to talk about next, that, okay, like if our focus is generating proofs or generating step sizes that are analytical, we can do that too using BnB-PEP. Now, how we do that? we do it the so-called potential function minimization approach. So in first order optimization, the standard approach to find proofs is through potential functions. What is a potential function? So it corresponds to an upper bound of the performance measure that we traditionally see, such as function value gap, distance from the optimal solution set, and so on. And we often choose this potential function carefully so that as n increases the upper bound of the potential function, it goes to 0. And often using some monotonicity argument and telescoping sum argument results in the convergent proof once we have shown that the potential function is monotonically decreasing as we are increasing our n. Now, what if we model, there should be an if here. What if we model all these things in BnB-PEP to find the best first order method to minimize the potential rather than fxn minus f star or the classic performance measure? If we do that, then this can systematically find the best algorithm with respect to the potential and also generate convergence proof. Okay, so let's take a look at a non-convex setup. So we will consider the set of the class of weakly convex function characterized by 2 parameter rho and L. So we say that a function f is rho weakly smooth, L subgradient bounded if it satisfies these 2 properties. So these are non-convex functions, but their abstract subgradient is bounded by this number L. So hence the name L subgradient bounded. And even though f is non-convex, if we add a sufficiently large norm squared term to this f, it becomes convex. So one simple example is the function x squared minus 1 absolute value. So as you can see, clearly this is a non-convex function. But if we add a sufficiently large regularizer to it, quadratic regularizer, it becomes convex. Okay, so for this setup, for the ease of exposition, we will consider first order method of the form xi plus 1 equal to xi minus h over rho f prime, which corresponds to the subgradient at xi. So xi minus h over rho f prime xi. So this is our first order method of consideration. Now, without loss of generality, we can scale the function by rho. Then if we define L tilde equal to L over rho, then we can just focus on the class of one weakly convex L tilde subgradient bounded function without loss of generality. Okay, so because this is a non-smooth function class, the question is how do we measure stationarity? So we can do it the so-called Morrow envelope, which is defined as follows. So this is the gradient of the Morrow envelope. So the Morrow envelope smooths a non-smooth function, and the gradient is defined as follows. So which is Morrow envelope by itself actually is smooth. So the gradient of the Morrow envelope f half that corresponds to the Morrow envelope smoothness parameter evaluated at x is equal to 2 times x minus the proximal operator f of f over 2 evaluated at x. So Morrow envelope has this nice property that it is smooth, and the small gradient norm of the Morrow envelope implies that we are near a stationary point. So in a way, this kind of acts as a unit potential function. Now, if we define this dummy iterate, that yk is equal to proximal operator of f by 2 at xk, then using the definition of a proximal operator, we can write down that yk actually will be equal to xk minus half f prime yk. And then we can write down the gradient of the Morrow envelope at xi very concisely using the subgradient of f at yi, where yi is this iterate that we have introduced here. Okay, so once we have done that, these are the questions that we are going to ask. That what is the best algorithm in this setup that will admit an analytical form? What would be this best analytical algorithm's convergence proof? And we will compare our findings with the previous state-of-the-art results from this paper by Davis and Drostevsky. So how we are going to model this problem? So first, we are going to define this potential function where bk is some unknown parameter and yk is defined here. We just introduced it a couple of slides ago. We want this specific initial condition to hold. Now keep in mind, everything that we are doing here, they will become constraints now. If we can show that our chosen potential function satisfy this specific inequality where ck is again an unknown parameter, then by doing a telescoping sum, we can show that the average Morrow envelope gradient norm squared, which is a measure of stationarity, would be less than equal to 1 over n plus 1 times this term, which contains both c and b. And L tilde is, remember, L tilde is essentially L over rho. Now, this is what we want to encode in our constraints. And note that the measure of stationarity is upper bounded by this term. So in this setup, our goal is as follows. So the best proof and the best analytical algorithm in this specific setup can be found by minimizing this upper bound that we see here, subject to the function class description that we have defined here and so on. Plus, we want this specific constraint to hold. So this will become one of the constraints. And all these things that we are saying, ck, bk, h, they are going to be our decision variables. Okay, so we actually encode these things very similarly using the recipe that I discussed earlier, and it leads to a BnB-PEP QCQP again. So one nice thing about this BnB-PEP QCQP compared to the generic worst case performance measure minimization thing is that here, if we look carefully, we will see that certain constraints are repeated over all the iterates. So this is the BnB-PEP QCQP, and you will see that these constraints that we are seeing here, all of them, they are denoted by this superscript k. So in other words, certain constraints, their structure, in a way, they are repeated over all the iterates that we started from 0 and continued until n. So this is going to be a crucial thing while we generate proofs. Okay, so at this point, we are going to minimize this using our BnB-PEP algorithm. And then what we do, we try to find the sparsest solution through the polishing approach. After we have solved this, we see the following pattern, that for all of these k's over the iterates 0 to until n, we see that only a few of the decision variables are non-zero, specifically these three, with the rest of the entries of the inner dual variable being 0. Not only that, when we look this symmetry in the optimal solution, that they are equal, there was another decision variable tau to star that is non-zero, where the rest of the entries of tau star k, they are 0. We see a lot of sparsity in the low rank z through trace minimization, and we see that only these are non-zero in the dual select matrix for the for kth iterate, and the rest of the entries of z star k being 0. Finally, we also see this specific pattern after we solve it. Once we have done that, once we have recognized this pattern through the polishing, we solve the BnB-PEP QCQP for single k. Keep in mind, for single k, it is being essentially the constraints. If we go back to the BnB-PEP QCQP, they are repeated over and over, right? Like the same constraints. So we actually focus on one single k. And once we do that, it looks of this format, right? And we put those 0 entries in this single k constraints. Keep in mind, this is a very small optimization problem now. And once we have put that sparsity pattern, it turns out to be much smaller, which can be solved then by hand. And this is the solution to the single k BnB-PEP QCQP. So what I am showing here, you can see that this is the optimal ck satisfies this inequality. Bk is controlled by this recursive scheme. These were my dual variables, the inner dual variables, and they actually satisfy these three equalities: bn plus 1 equal to 0 and cn equal to 0. So these are the non-zero entries, and also the rest of the entries of lambda tau are 0. Now, it turns out that if you have this solution, this corresponds to a completely feasible solution to the full BnB-PEP QCQP over all the k. So once we have that, that by itself actually is a proof, right? Why that is a proof? Because if we go back to this full problem, we have found one feasible solution to this problem. And any feasible solution to this problem would construct an upper bound, and this upper bound by itself gives you a rate that I'm going to show you soon. Okay. So the symbolic solution that we have found, that corresponds to a proof itself, but it does not look like a classical proof, right? Now, under strong duality and so on, the construction process of BnB-PEP QCQP does not have a loss. So we can actually go backwards to the original formulation and translate all the variables with respect to the original formulation to find a classical proof. How does that work? So remember, in this symbolic solution of the BnB-PEP QCQP, we have three dual variables, right? So lambda and tau. And each of these dual variables correspond to one inequality in the original primal formulation. So from KKT condition, what we can actually do, we can take all of these inner dual variables at their optimal solution. This is the symbolic solution that you see. So I am just taking them. I am finding what would be the corresponding inequality, because each of these inner dual variable correspond to some inequality in the primal formulation. So I take all those inequalities, I multiply all these inner dual variable at their optimal value times the corresponding inequalities, and then I add them together. If I do that, that by itself will lead to a classic proof. So this is the proof that I was showing you earlier at the very beginning, after 2-3 slides. And this was the proof, right? So of course they are very small here, but the rough idea is, again, recognize the optimal inner dual variables, find the corresponding primal inequalities, which kind of relates the functions interaction at different iterates. And then if you add them together here, which I'm showing you here, this will lead to the rate. So as you can see here. Now, of course, I have not found the optimal age. Now, the last thing to do is finding for what age this will be minimum, which can be done symbolically. And then the best step size that we can find analytically turns out to be this, where kappa is equal to R rho over L. In other words, is R by L tilde. So this will yield this specific rate, and it can be shown that this is strictly better than the previous rate found in Davis and Drustovsky's paper for large enough n. So I will conclude my talk now. So BnB-PEP is an unified methodology to find optimal first order methods for n iterations, and it can be applied to a lot of interesting setups. And as we have shown that, like in many cases, it is able to generate interesting and surprising results. My one advice for PEP practitioners is that often we are interested in finding a better algorithm. So in those cases, just applying the first two stages of BnB-PEP algorithm will suffice. And if you have any comments or question about the paper or code, please let me know. So thank you very much for listening to my talk, and I hope that I have been able to convey what BnB-PEP is about. And I hope I have been able to tell you a little bit about PEP itself, which in my opinion is a major breakthrough in optimization. Thank you very much. So let me stop the